Good afternoon, everyone. Today, our topic is stereochemistry and regioselectivity of elimination reactions. So, in previous lectures, we have discussed about the difference between E1, E2, and E1 CV reactions. These are three different mechanisms found in elimination reactions. Secondly, we have also discussed about why elimination reactions are preferred over nucleophilic substitution reactions. The third one is what factors favors E1 elimination reactions and E2 elimination reactions. So today we will discuss about the products formed in both E1 and E2. What is their stereochemistry and regioselectivity? Which product will be more dominated? These all depend upon the different mechanisms, whether the reaction is following E1 or E2 mechanism. So then moving toward E1 mechanism. So first of all, we will discuss about E1 elimination reactions. So I will give you a brief description about E1 elimination reactions. In E1 elimination reaction, the mechanism is two-step. In this, first of all, leaving group is removed. From here, leaving group is removed as Br negative. And in second step, there is abstraction of H positive. Abstraction of H positive by a base. Then it will give you alkene. Clear? So this is all about E1 elimination reactions. But the alkene here can formed. It depends upon the factors. What kind of factors? Let me tell you about the factors. First is kinetic control. The second is thermodynamic. If the product formed here is kinetically favored and thermodynamically favored, then that will be in the major amount. Let's discuss in more detail. So this is our first example. Look at the first example. In first example, you can see this is tertiary butanol, and it gives us eliminated product. Here, there is only one possibility. This is the methyl group, and there is removal of H positive from here and the OH from here. So it will give only one kind of alkene. And look at the second example. In this case, there is also one possibility, the removal of leaving group from here upon protonation of this group, and then abstraction of H positive. So it will give only one kind of alkene. So for some eliminations, only one product is possible. For others, there may be a choice of alkene products that differ either in the location or in the stereochemistry. So how the alkenes differ in the location? Look at the example number 3. In example number 3, if we compare the example number 2 and 3, in example number 2, here is the phenyl group. Clear? Phenyl group is this. Okay. And this is your cyclohexanol. As you can see, at this carbon, there is no hydrogen. This carbon has no alpha hydrogen. So there is no possibility of abstraction of hydrogen from here. So it left only with the hydrogen abstraction from this position and this position. So we have replaced this phenyl group with the methyl group. When it is replaced, the possibility of removal of hydrogen from this position also increases. So this is the alpha hydrogen. Here this is alpha carbon, and the carbons, the hydrogens attached to these positions are also known as alpha hydrogens. So I will write it in expanded form. H, H, and H. So this is possibility number 1 and this is possibility number 2. So first of all, your OH is removed as a leaving group. Then the second step is removal of H positive. H positive can be abstracted from first case. Then the product form is trisubstituted. If the H positive is removed from this alpha carbon, then the product form is disubstituted alkene. So this is the case in which the double bond is present at different regions. In this case, the double bond is present between these two carbon, and in this case, the double bond is present between two different carbons. So we will call these regioisomers because the region is different. The double bond is present in two different regions. So these are regioisomers. So the question is, which will be formed in major amount, whether trisubstituted or disubstituted? So we will discuss it on later. First of all, just understand the concept about what we are talking, regioisomers and stereochemistry. Then moving to the word stereochemistry. Here, stereochemistry. Hmm? Stereochemistry means when the molecule have different arrangement of atoms around a particular double bond or particular atom. See, look at this example number 4. In example number 4, this is just mark the numbering 1, 2, 3. Okay. So we have taken this example. This is your phenyl ring, and phenyl you can rewrite like this: phenyl OH 1, 2, 3. So this is the structure of this molecule. You can either represent the molecule like this. So upon protonation, what happens? This group will be removed. Okay. So the next is the abstraction of H positive. After removing this, there is formation of a carbocation. Here carbocation is formed. So there is possibility. There is formation of two products. One is trans, another one is cis. As this carbon and methyl, this is sigma bond. So the sigma bonds can freely rotate. These can freely rotate. So what happen on rotation? It will come to the downward direction. Clear? So that's why it can form cis product. What is the difference between trans and cis product? When the same groups are on the opposite sides, hydrogen, hydrogen, both are facing in opposite direction. So the product in which the same groups are in opposite direction, that isomer is known as trans isomer. So in this molecule, the hydrogens are facing in same directions. They are parallel to each other. So that's why this is the case when the groups are present in same direction. That is known as cis isomer. Clear? So these two are known as stereoisomers. Why stereoisomers? Because the spatial arrangement of atoms around these two centers in both molecule is different. So that's why these are called as stereoisomers. Clear? So the even reactions, there is three possibilities I have told you earlier. In first two case only one alkene is possible. So there is no formation of stereoisomers as well as regioisomers. So there is no possibility. Clear? But in second case, there is possibility of formation of regioisomers. And in third case, there is also possibility of formation of stereoisomers. So our question is, which stereoisomer will be formed in the major amount, either trans or cis? So we have to figure out these points, which will favor, which will be favorable product. So let's first discuss about the stereochemistry of products. Here, the last example we have discussed is leave it. Okay, then discuss with next example. Clear? Uh, hmm. This is a reactant. I have drawn it in the Fisher projection form. Fisher projection form. So basic you can also represent like this: COH, H, PH, C, Me, H, H. So this is the simple structure of these molecules I have drawn in this Fisher projection, Fisher form. So what is happening in this? This is our leaving group, OH group. Upon protonation, it get protonated and form OH2 positive. As in E1 elimination, first is removal of leaving group. So first step is removal of this leaving group. When this leaving group will be removed, it will form a carbocation. This is our carbocation, a intermediate. Clear? So upon formation of carbocation, this is also sigma bond. This can also freely rotate. Yeah. When this sigma bond rotates, what happens? See, when this sigma bond rotates, pH, H, H, Me, H, H. So the methyl group will be in downward direction. Here, these two will be interchanged, methyl and hydrogen. They will interchange their position. So here the methyl group has position in downward direction. Here. So that's why there is formation of two isomers due to the free rotation of this carbon-carbon bond because this is single. So there is possibility of removal of hydrogen from here in this form also, and here is the positive charge. Okay, hydrogen can be abstracted from this form also, like this. Yeah. So what is the difference between both these two structures? In the first case, vinyl group and methyl group, they are lying in opposite directions. Clear? In second case, the phenyl group and methyl group are present in same direction. Clear? So which will be form the major product? So look at the transition states of both carbocations. This is first possibility and this is second possibility. So by comparing the transition state of both the intermediates, we will be at some conclusion. So this is the first case in which hydrogen is abstracted from here, and see what is happening in this. Water molecule is coming and attacking on hydrogen. Then in transition state, we show the bonds are getting broken and are forming. So these are represented in dotted lines. Look at the bond between this carbon and this carbon. So here pi bond is get formed. So I have drawn a dotted line, and the bond between this carbon and hydrogen is getting broken. So I have also formed a dotted line. Clear? The molecule of water is attacking on this hydrogen. So this bond is also presented in dotted line. And upon attacking, it will lose its electrons. So that's why I have represented positive charge on this oxygen. So transition state is only that state in which the bonds are shown in dotted line, and the bonds only those are shown in dotted line which are formed and broken. Clear? So look at this transition state. In this, these two groups are on opposite sides. There is no steric hindrance in this transition state, and the H positive will be abstracted from here very easily. So as well, this is lower in energy. Clear? If we draw its energy profile diagram, then it will be like this. This is the transition state. Here is the product. And what will be the product? Methyl. So these phenyl group and methyl are in opposite direction. So this is the trans product. And this is your energy. So you can see it is at this position. So it has lower energy. If we compare it another case, look at the another case. In this case, the methyl group is in downward direction. Clear? So I have drawn its transition state, pH, pH, carbon, and the methyl group in downward direction, and the hydrogen is abstracted from here. So water molecule from here is abstracting H positive. So as in previous case, I have shown the molecules, the bonds in dotted lines. Here also presents the bonds in dotted lines. Clear? So you can see there is steric hindrance between these two atoms, these two groups, sorry, not atoms, groups. Clear? Because they lie very close to each other due to their presence in same direction. These are causing steric hindrance. So that's why it has higher energy as compared to this intermediate. I have shown this energy difference. Clear? You can see clearly the energy difference between these two transition state. This is at lower energy, this is at higher energy. So due to its higher energy, the product formed from this will be also in higher energy. So if we draw its energy profile diagram for this also, the energy profile diagram will look like this. Yeah, and the product formed is this. Yeah, the alkene is cis. So now see the difference between the energy level of two molecules. The energy of the trans molecule is at this position, and the energy of cis molecule is at this position. If we check the energy like this. So this is the difference between the energy gap of two molecules. So cis have higher energy as compared to trans. So only those molecules will be favored which have low energy. So that's why I use the term kinetic control. The intermediates which have low energy will be favored more. Clear? The second is the product which are more stable. More stable means thermodynamically stable. Thermodynamically more stable means when the product is formed, one is trans, another is cis. So in trans, the molecules are in opposite direction, so it has low energy. So it is thermodynamically stable. This is thermodynamically less stable. Here is the factor of kinetic control. The energy of this transition state is less as compared to this. So this is more stable. That's why the even elimination reactions favors the product which are kinetically and thermodynamically more stable. The more stable product means which has less energy. Yeah, less energy means more is the stability. So that's why even reactions form stereoselective product. Now, what is the term stereoselective? As we can see in this case, the product, this is trans, this is cis. The trans product is formed in 95% yield and this is formed in 5% yield. So this is in major amount. Clear? Okay. Whatever is the stereochemistry of isomers means reactant. You can choose whatever is the stereochemistry of reactant. It will form only one kind of product, that is trans, which is more stable. So that is the meaning of stereoselectivity. Okay, means it will give only one kind of product. Let us discuss the definition of stereoselectivity. Stereoselective reactions give one predominant product, that is the trans in case of even reactions. Okay, so in this case, even reactions, trans, the groups are present on opposite sides. That's why that is more favored because there is less steric hindrance also. Because the reaction pathway has a choice. Clear? Because the once the carbocation is formed, it depends upon the abstraction of hydrogen, H positive. Either the pathway of lower activation energy is preferred, means kinetic control, or the more stable product is preferred, that is thermodynamic control. We have discussed both kinetic control and as well as thermodynamic control. So even reactions are stereoselective, means it will give only one type of product in major amount, that is trans. Clear? Now we will discuss about the regioisomers, regioselectivity. So then heading toward the regioselectivity. Okay. Even reactions are regioselective. Clear? Which kind of product we will get, as we have discussed the example over here. This is the example of regioisomers. One is forming trisubstituted alkene, another is disubstituted. But what is the major product? The alkene, which is trisubstituted. That is the major product here. This is the major product. So why we are getting trisubstituted alkene over disubstituted alkene? So this is also Satzeff rule. According to Satzeff rule, the alkene that will be formed, which is highly substituted. Clear? So here, first of all, what is the meaning of highly substituted, less substituted and highly substituted? Then coming back to example, see, this is carbon number 1 and carbon number 2. This carbon number 1, it is attached to alkyl group. From this side, it is attached to second alkyl group. The carbon number 1 is attached to 2 alkyl group. Clear? Okay. And the carbon number 2, this is attached to 1 hydrogen and 1 alkyl group. So this is attached to 1 alkyl group. Clear? And in second case, what is happening? Carbon number 1, it is attached to 2 alkyl groups. In carbon number 2, it is attached to 2 hydrogens. There is no alkyl group. So this is more substituted, in which the carbons are attached to more alkyl groups. That is the meaning of substitution. Here are the 3 groups. Carbon number 1 and attached to if we are summarizing the total all over. So we can start to discuss individually. See the carbon number one, it is attached to only two groups. Carbon number one is attached to two alkyl groups. That is same in both cases. But see the carbon number two. Carbon number two, it is attached to one alkyl group and there is no alkyl group. So that's why this is more substituted. This is highly substituted. That is, we are using term tri-substituted and it is attached to two alkyl groups. So we are using di-substituted alkene. It is more favorable. Clear, the formation of tri-substituted alkene is more favorable according to Sartsef rule. So according to Sartsef rule, the alkene only will be formed which is highly substituted. So let's understand why the highly substituted alkene will be formed. Clear? Okay. I have chosen three alkenes. This is a simple alkene, ethene. In this, the carbon number 1 and 2 both have 4 hydrogen atoms. And this is second example. This is propene. 1, 2, 3. In this, carbon number 2 is attached to one alkyl group. Clear? Then look at the another example. 1, 2, 3, 4, 5. This is pent 2E. In this, carbon number 2 is attached to one methyl group and the carbon number 3 is attached to also methyl group. So there are two alkyl groups in this. So as I am moving from left to right, the number of alkyl groups have been increasing. So substitution is increasing from left to right. Clear? So let's draw this structure like this. Clear? There is a pi bond. Pi bond is formed when the bonding orbitals are overlapping to each other. So I have been showing here anti-bonding orbital, pi star orbital instead of pi orbitals. So these are anti-bonding orbitals. Anti-bonding orbitals, they have electron density in different directions. So that's why there is no bond formation between anti-bonding orbitals. They are showing no overlapping. Clear? So I am showing there is no pi bond because here I am representing pi star orbitals, anti-bonding orbitals. Clear? See, in second case, this is carbon number 1, carbon number 2. The carbon number 1 and 2, there is the pi star anti-bonding orbital. And this methyl group, this is the carbon and this is the or p orbital of carbon, and it is overlapping with one of hydrogens of this CH3, and these are two another hydrogens. And these two hydrogens I have presented in the solid lines. Why this orbital I have presented in the green color and shown it this in the form of orbital? I am showing only those orbitals in green color which are parallel to pi star antibonding orbitals. Look at this. This is parallel to this orbital. So these two are not parallel to this pi star antibonding orbitals. So I will draw only those orbitals which are parallel to pi star antibonding orbitals. Clear? So third is pentene. So this is carbon number 3 and carbon number 2. Clear? The carbon number 1. It has 3 hydrogens. This is the carbon, and I have drawn its one-off orbital which is parallel to this pi star antibonding orbitals, and these are another 2 hydrogens. So then this is carbon number 4. Here is the carbon number 4. The 2 hydrogens are like this. And this is carbon number 5. Carbon number 4 and 5. I have drawn the orbital of these carbon and carbon bond because these are parallel to pi star antibonding orbitals. So these are another three hydrogens of carbon number 5. These are not parallel to this pi star antibonding orbital. So I have not represented here in this forms. I have shown only those orbitals which are parallel to pi star antibonding orbitals. Why I have drawn only these orbitals? Because this is the bond between carbon and hydrogen. One carbon and hydrogen, sigma bond. Clear? This is carbon and hydrogen sigma bond. Okay. This is in second case and this is in third case. In first case, there is no carbon and hydrogen sigma bond between substituted molecule. Okay. Means there is no parallel. You can say there is no CH bonds parallel with pi star. You can say like here in first case. In second case, there is one CH sigma bond that is parallel to pi star antibonding orbital. In third case, there is one CH sigma bond. Another one is one CC sigma bond. CC sigma bond. So more number of CH and CC sigma bonds, they will more interact with these pi star antibonding orbital. When these will interact more with pi star antibonding orbital, so the molecule will be more stable. Yeah. So increasing substitution allows more CH and CC sigma star orbitals to interact with the pi star orbitals. So this is similarly, it is also true in the case of carbocation. Clear? In case of carbocation, when its empty p orbital can interact with the filled orbitals of parallel CH and CC bonds, that carbocation will be more stable. So both this rule is valid also in case of the pi orbitals. So empty pi star antibonding orbital can interact with the filled orbitals of parallel CCH and CC bonds. The more CC or CH bonds there are, the more stable the alkene. Here, when there are more interactions, it will be more stable. So look at the transition states. So here is the example. Here is the H. Okay. So the first is the protonation of this OH group. When this OH is protonated, it is forming OH2 positive, and then it leaves from here. Then there is formation of a carbocation. Clear? So in this case, there are two possibilities. First possibility, second possibility. In first possibility, when the hydrogen is removed from here, means hydrogen means H positive is removed from here. In the second case, when H positive is removed from methyl group. Let me draw it in expanded form. In expanded form, what is happening? This is your methyl H CH2 H and this is the carbocation. So these two structures are same. I have just presented this methyl group in the expanded form like this. So there is possibility that the hydrogen can also be removed from H positive, can be abstracted from here. H positive can be abstracted from here. Look, sorry, this is a wrong arrow. When H positive is abstracted from this carbon, the bond will form here. So the arrow will goes in this direction. Here, so there are two possibilities. Let us explain through the energy profile diagram. So I have drawn the earlier structures I have discussed with you here. This is your hydrogen 1, this is hydrogen 2. There are two possibilities. So in first case, methyl groups, two methyl groups, and this hydrogen will get abstracted by a water molecule. So this is the transition state. In this, all the bonds which are forming and get breaking are presented in dotted lines again. So this is a double decker presenting transition state. This transition state has lower energy. Why this transition state has lower energy? So in this partial double bond has three substituent. Clear? So there is formation of double bond. Okay. In the next step, but in transition state, I have presented this partial because this is the transition state. The bonds are in the dotted line. There is more stability of this carbocation here. Here. So look in second case, what is happening? This carbocation. And there is carbon, the partial double bond between these two carbon. Okay. And this carbon is attached to hydrogen, and this carbon is attached to one alkyl group. We will consider this one because there is one hydrogen also. Okay, so this is only one alkyl group. But here, this is one alkyl group, this is another alkyl group, this is third alkyl group. Okay, this is between these two carbons. So there are three alkyl groups. Here is only one alkyl group. So it has only one substitution. So this has high energy. High energy. So transition state is less stable here. So look at the products, how the products are forming from these transition states. From first transition state, the product form is highly substituted alkene. Clear? So this is a product from here. This is tri-substituted alkene. And this is the energy level of the product. And this is the energy level of the transition state in this case. In another case, when there is only one substitution, here is the energy of transition state. Okay, and the product from this transition state is at this energy level. Means it has higher energy when we compare these two products, tri-substituted and monosubstituted product. Monosubstituted product at this stage, and there is the energy difference between these two products. Mono has higher energy as compared to tri-substituted product. So that's why highly substituted product is formed more easily and faster as compared to monosubstituted product. So this is the case of E1, which form trans and highly substituted product. The highly substituted product, this is the rule according to Satsef. There is a scientist, he has given this rule and explained the theory behind this, why highly substituted products are get formed here. So we have discussed in case of even elimination reactions, what will be the stereochemistry of product, which product will predominate. So I will give you just brief overview of E2, then we will discuss it in next lecture. But let me explain about E2. In case of E2, first of all, what is happening? H, Br. So there are, you can see substitutions R3, R4. In this case, both abstraction of H positive and removal of leaving group are simultaneously. Here, both are removed simultaneously. So this is a one-step mechanism. So in this case, as mechanism is different, that's why stereochemistry of product is also different. Here, so in case of E2 we have been using the word stereospecific. It is also regioselective, okay? But we will know in this case which product is formed, highly substituted or less substituted. Clear? So there are two possibilities. One is highly substituted product, another is less substituted product, but which will be formed in the major amount? This is our question about that is concerning question. The another one, we have been using the term stereospecific. In case of E1, we are using the term stereoselective. Stereoselective. Stereoselective means whatever the reactant is. Clear? The product only will be trans. Only one product will be formed. That is there because it depends upon the uh, mechanism. Here there is a choice of kinetic control and thermodynamic control. But in case of ECHO, there is word we have been using stereospecific means. Stereospecific means if we are choosing a reactant which have stereochemistry, which have particular stereochemistry. Suppose this is 1, it will give trans. If we have been choosing the product, the reactant, which have different stereochemistry, that is reactant number 2, then it will give cis product. Means the stereochemistry of reactant and the product will be same. It depends upon what kind of reactant we have been choosing. Clear? If the stereochemistry of reactant is also cis, almost cis means we cannot use the term here cis, but the groups are present in same direction, then the product here we will be get in where the groups are present in same direction. If here in reactant the groups are present in opposite directions, then the product we will get in which groups are in opposite directions. So that's why it is called stereo specific. Particular reactant will give particular product. Where there is no predominancy of stereoisomers over here. That's why E2 gives stereospecific products. Stereospecific reactions lead to the production of single isomer. As a direct result, the mechanism of reaction and stereochemistry of the starting material. So it depends upon the stereochemistry of starting material. There is no choice. The reaction gives a different diastereomers of product from each stereoisomers of the starting material. Okay, so I have already told to you if we have been using particular stereoisomer, it will give its kind of diastereomer. Okay, so in case of E2 transition state, it form anti-periplanar transition state. So as in both the groups are removed only in one step. So what is the meaning of anti-periplanar? Means both the groups which should be removed that lie in different plane, they will be anti to each other. So that's why we have been using term anti-periplanar. Yeah, like H is here and Br is here, so they should be anti. Only that's in that case E2 elimination is possible, and it will give you a product. Clear? So I will discuss this in the next lecture. If you like this whole video, please like it, share and subscribe. If you have any kind of query, please comment in the comment section. Then I will give you more clarification if you have any kind of question. Thank you.